Hi everybody, my name is András Papp, and I'm going to be talking about the stabilization time of graph processes, presenting a joint work with Roger Wattenhofer. So by graph processes, we refer to a setting where each node of a graph is in a given state, represented by a color, let's say for simplicity only two colors, black and white, and occasionally nodes change their state based on the states of their neighbors. And one of the most popular examples of such a process is a majority process, where nodes want to switch to the color which is more frequent in their neighborhood. So for example, this node looks around, sees that it has more black neighbors than white, and therefore decides to switch to the color black. And of course, this is a process which has various applications in many different areas. For example, it can model the spreading of political opinions in a social network. So for example, if this guy looks around and sees that most of his friends are voting for the opposite party, then he might decide to switch to the other opinion, which then might prompt one of his friends to also switch to the opposite opinion. And then maybe this guy looks around and decides to make a change in the other direction, and so on. Or another example is the adoption of different social media platforms. So, for example, if somebody is using Twitter but sees that most of his friends use Facebook, then he might decide to switch and also use Facebook instead. And there are many more examples in other branches of science. So in the base version of a majority process, every node is either black or white. And for example, a white node switches to black if it has more black neighbors than white. However, in many cases, this is not a very realistic model of applications, since if, for example, you have 100 friends with 51 of these voting for the opposite party and 49 voting for the same party as you are very unlikely to change your well-established opinion for such a minor difference. Therefore, what we'll actually study in this talk are proportional majority processes, where you only decide to change your opinion if the difference between the black and white neighbors is at least the lambda portion of your degree for some parameter lambda of the process. And since we consider the case of only two colors, we can also express this equivalently by saying that you only switch to black if at least the 1 plus lambda half portion of your neighbors are black. So this step is nothing more than basic arithmetics with this equation. For example, saying that you have 40% more black neighbors than white neighbors is equivalent to saying that at least 70% of your neighbors are black. But both formulations are nice to know, since the upper one is a more natural way to express our results, and the lower one is probably a more intuitive way to understand this proportional case. And while lambda goes from 0 to 1, this 1 plus lambda half goes from 50% to 100%. Another similar kind of process is a minority process, where nodes switch to the color which is less frequent in their neighborhood. So for example, in a wireless network, devices want to select a frequency which is different from their neighbors. So in such a minority process, this node has two black neighbors and one white, so it decides to pick the color white. Then this node switches to black, then this node switches to white, and so on. So the proportional majority and proportional minority processes behave very differently from many perspectives, but in this talk we'll be able to analyze them together by abstracting away the colors and expressing most of our statements in terms of conflicts. In case of a majority process, we can define a conflict as an edge that has different colors on its endpoints, and in a minority process, a conflict is an edge that has the same color on both of its endpoints. And then in both settings, the goal of the nodes is to decrease the amount of conflicts on their incident edges. And the node is switchable if and only if the number of its incident conflicts is at least 1 plus lambda half times its degree. So for the rest of the talks, we are always going to show examples for majority processes, but the same results can easily be carried over to minority processes too. So what we're interested in throughout this talk is the stabilization time of these processes. That is the number of steps it takes until the switching stops and no node wants to change its color anymore. And we're going to study this question in the sequential model, where in each step exactly one node switches its color. And this is often a good approach because in many applications, you are highly unlikely to switch your color at the exact same time as your neighbors. For example, to change your political opinion at the exact same time as your friends. And otherwise, even in simple graphs, this could lead to situations where both nodes want to change their color, and if they do it at the same time, then this gives a similar situation. So it could happen again and again, going on forever, which is quite unrealistic in these applications. So our main goal is to find the worst case stabilization time of these processes. That is the maximum number of steps the process can take over all graphs on n nodes and all initial colorings of these graphs and all possible orderings of switches. So let us first get a general idea of how large we should expect the stabilization time to be. For this, let's first look at the case of the smallest possible lambdas that are very close to zero, or in other words, when nodes already switch color if slightly more than 50% of their neighbors are opposite colored. First of all, even in this case, it is easy to see that the number of steps is upper bounded by n squared, and this is because when any of the nodes switches to the majority color in its neighborhood, then this means that the number of conflicts on the incident edges strictly decreases by definition, even for a very small positive lambda. So the total number of conflicts in the graph decreases in every step of the process, and since the graph has only quadratically many edges, it can have at most quadratically many conflicts initially. So if this strictly decreases in every step, then the number of steps is at most O of n squared in any case. On the other hand, previous work has already shown that in case of basic majority processes, so when lambda is essentially zero, there exists a construction where stabilization can indeed last for almost quadratically many steps. So for lambda values close to zero, we should expect that the maximal stabilization time is more or less in the magnitude of n squared. And the other extreme is the case when lambda is as high as 1. That is, when a node only switches to the opposite color if every single one of its neighbors have the opposite color. In this case, on the one hand, we can show that stabilization time is at most linear. Assume that a node switches to black at some point, which means that all of its neighbors were black. So in this case, the node itself cannot switch after this point due to its neighbors, since they have the same color as the node, and the neighbors also cannot switch due to the node, since they have at least one neighbor of the same color. So the node and its neighbors essentially remain locked in this situation forever and can never switch anymore. And this means that each single node can switch at most once in such a process, and therefore we can never have more than n switches. On the other hand, if we connect two simple nodes of different color, then of course the white one can switch to black since all of its neighbors are black. And if we simply take n half independent copies of this component, then we can switch the white nodes in this graph in any order of our choice, which is already a process of n half steps, so we also have a linear lower bound on the stabilization time. So as a function of lambda, we should generally expect that the maximal stabilization time is quadratic when lambda is around 0 and linear when lambda is 1. And our main result in the paper is showing that the stabilization time follows a continuous transition between these two extremes, and we have found that this transition can be described by an interesting non-elementary function f. So as you can see on the slide, this function has a rather complicated definition, which we'll try to break down to smaller parts later. But for now, let's just note from the figure that this is a function that's continuous and convex and decreases from a value of 1 to a value of 0 as lambda goes from 0 to 1. So for this function f, the results that we show in the paper is that for any positive epsilon, on the one hand, the stabilization time of the processes can be upper bounded by n to the 1 plus f lambda plus epsilon for any lambda value. And on the other hand, there exists a construction where the process indeed lasts for n to the 1 plus f lambda minus epsilon steps for various lambda values. So as lambda goes from 0 to 1, this n to the 1 plus f lambda indeed describes a transition from quadratic to linear behavior, and this allows us to almost tightly characterize the maximal stabilization time of the process. So before we jump into the analysis of this function f, let's first try to understand the basics of this proportional setting. So one thing that follows from the very definition of the proportional process is that since a node only switches to the opposite color if the difference between the opposite colored and same colored neighbors is at least lambda times its degree, every such switching decreases the total amount of conflicts in the graph by at least lambda times the degree. right? If you switch when you had conflict with 70% of your neighbors, then now you only have conflict with 30% of your neighbors. So 40% times your degree conflicts are lost from the graph. So first of all, if you want to maximize the stabilization time, then it is somewhat clear intuitively that we should always switch nodes when they are exactly at this threshold, because if nodes have even more conflicts when switching, then this removes even more conflicts from the graph and the process will finish earlier. Also, since the amount of conflicts lost in a switching depends on the degree, it turns out that low degree nodes and high degree nodes will have a very different role in the process. Low degree nodes only waste a few conflicts when switching, so we would want most of the switches to happen at low degree nodes in the process. But on the other hand, low degree nodes can only have a few conflicts on their incident edges, so if we only have low degree nodes in the graph, then we can barely have more than linearly many conflicts already in the beginning. So we also need to have high degree nodes in the graph in order to have a lot of conflicts initially. Altogether, the best case scenario would be to have a set of linearly many nodes of linear degree, which can therefore store up to quadratically many conflicts initially, and then use these quadratically many conflicts to switch another set of constant degree nodes that only waste a constant amount of conflicts at each switching. If we could do that, then this would allow the number of switches to go up to as much as n squared. However, it is not possible to take these n-squared conflicts and directly send them to the constant degree nodes, so in fact we'll need to use a range of intermediate levels to propagate these conflicts from top to bottom, and the stabilization time will depend on how efficiently we can do this propagation, that is, how many conflicts we waste in this process. So actually what the function f describes is the efficiency of this propagation process. And so our optimal construction will consist of a range of different levels with log n such levels altogether and about n over log n nodes on each level. And as we follow the direction of this propagation, so as we go from the top to the bottom, the levels will have lower and lower degree, but the nodes and the levels will execute more and more switches. So after this brief overview, let's go into more detail and try to understand this function f. The first thing you probably noticed is that the function is expressed in terms of another parameter phi. So what this phi expresses is essentially the ratio of neighbors that we use as inputs and outputs at each node. Basically, since switching is a wasteful process, we only want the conflicts to flow in one direction in our construction from high degree nodes to low degree nodes. So even though the process definition is symmetric, in the optimal construction, each node will use its incident edges in an asymmetric way. That is, we select a phi portion of a node's neighbors and mark them as output edges, and mark the remaining 1 minus phi portion as input edges, and then we make sure that in the process, the node only consumes conflicts from its input edges when switching, and produces new conflicts on the output edges when switching. So essentially, it will always be the input neighbors of the node that force the node to switch to the opposite color, and it will be the output neighbors of the node that are forced by the node to switch to the other color. And so this main parameter phi that will be the key of the whole process is the portion of neighbors that the node uses as outputs. Now, if we look at this expression in the denominator, this is already something that follows quite intuitively from this base idea. Since upper neighbors are inputs and lower neighbors are outputs in our level-based construction, this means that every node will have phi portion of its edges going to the level below and 1 minus phi portion of its edges going to the level above, which means that the degree of nodes will always decrease by a factor of 1 minus phi over phi in each new level of our construction. And this shows that we can indeed add logarithmically many levels to the graph until the degree decreases from linear in the uppermost level to a constant in the lowermost level. Now, the slightly more complex part is the expression in the numerator. And to get an intuition behind this, we'll have to check in a bit more detail what we need in order to switch a node V some s number of times. So first recall that each switching wastes lambda times degree of V conflicts. So in order to switch the node s times, the inputs of the node need to put altogether lambda times degree of V times s conflicts on the incident edges of V. Furthermore, note that when V propagates a conflict to its outputs, then the outputs will remove and further relay this conflict when they switch. So for the next switching, V does not only need lambda times degree of v new conflicts to reach the switchability threshold again, but it also needs some extra conflicts to replace these conflicts that have been consumed by its output neighbors. So let us see what this formula implies. Intuitively, our main goal in the whole propagation is to take the conflicts that are initially scattered on n squared edges and put these conflicts on much fewer edges in multiple rounds. So if v switches s times, then the best strategy is to send the conflict to each output every single time. Otherwise, we could just use the inputs more wisely by having fewer output edges and sending more conflicts on them. So this means that the number of output conflicts in S switches will be this much, which we can shorten into this form. On the other hand, the optimal strategy is to distribute the input conflicts on the input edges in a way that is as balanced as possible. So assume that each input node gives S prime conflicts to V, which means that the total number of input conflicts is this much. Now we can just take away the degree and do some reorganization, and we get that if the input nodes switch S prime times, then S can switch at most this many times. So the number of switches increases essentially by this 1 minus pi over lambda plus pi factor. So that is where this expression comes from. And this already kind of explains how the whole formula of f is obtained. We know the increase in the number of switches per level, and we know the number of levels. So this expression describes the number of switches we have on the last level. And then this can be reformulated into this. And if you recall the definition of f, this is upper bounded by f by definition. And this also shows that we can only attain this maximum if we choose phi as the argmax of this expression. So for each lambda, there exists an optimal choice of output ratio of pi, which gives you the best number of levels and the best increase per level to reach this highest possible number of switches by the bottom level. We can also have a look at this optimal choice of phi for each lambda, but of course this is also a function that, well, at least to our knowledge, cannot be expressed in an elementary way, since otherwise this would, of course, also provide a simpler definition of f that avoids this maximization. So now that we know that the nodes on the bottom level can switch n to the f lambda times, we only need to recall that each level of our construction has linearly many nodes, apart from a logarithmic factor. So the sum of switches on the bottom level is about n to the 1 plus f lambda this way. And in fact, one can see that the remaining levels are simply negligible besides this. So this is how our upper and lower bounds are obtained. So I hope that this already gives you the base idea of what happens in this setting. And of course, both the upper and lower bound proofs are much more involved in practice, and you can check out the details in the paper. And in fact, the base idea of the upper bound proof can be nicely expressed in terms of a potential function argument. So if there are C conflicts propagated in one direction on a single edge throughout the process, then we can define the potential of this edge as C to the 1 over f lambda, and then one can show that this potential is either conserved or lost throughout the process, but no node can create more output potential than the input potential it receives. And then initially we have n squared edges with at most one conflict, so there's essentially at most n squared potential in the system. And if you want to switch n nodes s times, then this expression is upper bounded by n squared, with all the constant factors ignored for simplicity. And then you can remove an n and get an upper bound on s. Or in a more general form, if you look at the nodes that have degree d, then these nodes need some constant times d conflicts for each switching. So then again, after reorganization, these nodes can switch at most this many times. And for lower bound proof, the base idea of the construction is this level-based structure that we have already discussed, with logarithmically many levels and n over log n nodes per level. And as we have seen, if we choose the optimal phi value, then this already allows us to reach the upper bound if we can increase the number of switches by this factor in each level of the construction. However, this turns out to be a rather big if. So while the general structure of the construction is rather clear, it turns out that designing the connection between the levels that ensures this is a very serious combinatorial challenge in itself. So recall that choosing the outputs is not a problem, since for the optimal propagation, each output has to switch every time after a node switches. On the other hand, between any two switches of the node, we have to switch exactly a lambda plus phi over 1 minus phi portion of the inputs in order not to waste any conflicts unnecessarily. Furthermore, these subsets always have to be of the right color, that is, switch to the opposite color that we currently has, and we have to do it in a balanced way among the inputs, such that in the end all inputs have switched the same number of times altogether. And finally, in order to be able to argue about levels in general, it would be best to do all this in such a way that the behavior of each level is very similar. So if a level executes a given sequence some number of times, then the next level executes the same sequence, but even more times. So new levels always essentially do the same thing, but with more repetitions. And creating a gadget that provides such a convenient connection between the levels is also needed to nicely prove that we can really implement such a construction. And this is not only a bound that can be reached in theory. In the paper, we also discuss this combinatorial problem in detail, and we show how to create such a connection gadget for a range of lambda values. In particular, our solution covers all the lambda values below approximately one half, and also some higher values above this threshold where this increased parameter is nice in the sense that it can be expressed as a fraction of small integers. Finally, we point out that with a small trick, one can avoid this combinatorial problem and show an almost tight lower bound for any lambda value by essentially adding a dummy relay level between any two levels. But this technique comes at the cost of wasting some extra conflicts at these dummy levels, so it introduces an extra waste factor into the formula of f and leaves some gap to the optimal upper bound. So one natural opportunity for future work is to solve this combinatorial challenge and come up with a lower bound gadget for any lambda value. But of course, there are many other open questions left in this area. For example, there are various ways to introduce randomization into these processes, and then one could study the stabilization time of these randomized settings. And with that, I thank you for your attention, and I'm happy to answer any questions in the Q&A session.